Welcome everybody. First I'd like to start off by thanking ACAMP for inviting me to speak today and all the sponsors of the event. I guess one way to put it is now for something a little completely different. I represent basically the University of Alberta and a few other functions that I'll talk about this morning. But basically I'm a strange professor. I talk about this a lot. My position at the university is a little different in that I have a 40% extension component built into my actual academic appointment. I'm cross-appointed with the Bioindustrial Technologies Division of Alberta Agriculture and Rural Development. So it's really an organization set up with half engineering and half business development to help build a bioindustrial sector in Alberta. So a little bit today I'll be talking about that, but some of the other hats I wear, I won't go into them in detail, is I sit as the chair of the Agri-Food Discovery Place Management Board, which is a 5,000 square meter pilot facility on the university's South Campus to develop bioindustrial applications for chemicals, food, and some food safety functions as well. And I guess the last hat I have is as director of the newly formed Biorefining Conversions Network, which was launched about a month ago. Again, that's to bring and cluster together the bioindustrial researchers and activities in the province. Today, I'll try and give you a snippet of what's going on in the province, and some going down to one specific example. But basically, the program we're looking at is how do we take biomass in Alberta, whether it's animal, agriculture, forestry, and convert it to interesting chemicals and fuels. Some of the projects I'm working on, I'm kind of feedstock agnostic. A lot of people tend to be plant people or animal people or forestry people. Again, my background is I'm an industrial microbiologist that spent a little bit too long in chemical engineering working with Syncrude and their upgrading group. So we work on everything from grains and lipids, protein fractions, but we look at how we convert them to industrial chemicals. Again, these are precursors to replace what happens with the traditional non-renewables, things like ethylene for polymer applications, industrial foaming agents, and fuels, solvents and high cetane. So really, we're trying to take what's new and renewable and convert it and replace the stuff that is not. And again, moving an economy from one that's non-renewable to one that is renewable, and trying to, in a way, reinvent the forestry and agricultural sectors, which are key components of our economy that have been under siege for at least a decade or so. Again, a couple quick terms. I won't spend a lot of time on this. Being an academic, crushing to 15 minutes means moving pretty quick. Bioproducts, again, these are anything coming from natural sources in a way that we kind of exclude pharma from this, this is more of a functional definition. And biomass, any organic material we can harvest on a renewable basis. A couple stats, 224 billion tons a year of renewable biomass, 15% of the energy used around the world. Unfortunately, 85% of that is of the traditional, let's burn it in the oven, burn it this way, burn it that way. So we're looking at ways of changing this to a more sustainable system, but we're also, we're looking at 35% of the energy needs of developing countries. Not everybody has the oil sands that we have up north. Okay, so we take waste from all these, our byproduct streams from the traditional sectors. Municipal wastes are included, that's not my core area, but we look at how we move them into what's called a biorefinery. And I'll come back to that in a minute. You've all heard about national policy goals and biofuels, and we can get into food versus fuel endless debates. The reality is, if you take it from a biorefining standpoint, you look at it as a feedstock, you break it down into its different fractions, and then you get maximum use from each of those fractions based on what your values are. It becomes a completely different debate. Okay, not any one crop or biomass needs to go directly to food. There's chances to break it down and capture maximum value, and I'll spend a little bit more time about that in a second. But right now we're looking at 5% renewable fuels by 2010, primarily ethanol nationally, 2% biodiesel by 2010, and longer range goals. Interesting enough, Alberta is just in the formative stages. We're finalizing our policy that will require all blended material to be 5% ethanol, 2% biodiesel, and on top of that, Alberta has the kicker that it has to have a 25% greenhouse gas reduction over a non-renewable fuel that it's replacing. So that means corn from the U.S. fired off coal facilities or other ones would not qualify. So there is going to be a big push very quickly in a huge market in Alberta, and BC is very similar. Manitoba just announced a similar policy. So it is coming. Going back to the biorefining model I talked about, we want to take our biomass and fractionate it. It doesn't make sense to think of any biomass as strictly a precursor for fuel, precursor for food. It makes a lot more sense looking at what it's made up of. On a very simplistic form, biomass can be characterized as fats and oils, carbohydrates and sugars, proteins and amino acids, and then a bunch of other smaller trace components. If you think of it this way, it doesn't make sense to send all of these to one biofuel technology. or to food. We have opportunities to use things like fats and oils for fuel technology. We actually have some patents on converting fats and oils directly to hydrocarbon fuels. So we got away from biodiesels. We're going to the second, third generation. Carbohydrates and sugars, high energy molecules, good for fermentation, also good for human consumption. Proteins and amino acids are terrible components for food applications. They tend to be functioning in terms of enzymes and structural components in living biomass. They make a lot more sense as food additives or potentially protein-based polymers, etc., structural applications. I'm just going through these pretty quickly, but you could see in the biorefinery, we take very much like we would in the traditional chemical biorefinery. You start off with the biomass, you figure out how you fractionate it into major components, and then convert them to the things that are of highest value. You don't do what the US primarily did, which is take a biomass, convert it to ethanol, feed the rest to cows. If the ethanol price goes down, you crash your industry. A much better approach is to take a biorefining approach where we get each fraction, we have multiple product portfolios, etc. The problem with this, and where I'm coming with today, is we have an issue. Everybody looks at biomass, looks at the list of table of contents of what's in there, projects a market price of each of those components, and then tries to start businesses. On the research side, everybody seems to want to be studying the conversions, which is where I live, or on the final application. What we've missed is that it's a huge effort to separate those fractions into their various components and to set up reactive systems to convert it and allow us to separate. And that is really the critical thing that keeps biomass from being really competitive with the non-traditional, is that separation step that everybody seems to skip over in their mind. And it has huge applications and opportunities. I guess call this a call for collaborators in the area of nanotechnology, being able to sort molecules, separate fractions, etc. Again, oil sands, I won't go through here any time, but basically our traditional oil sands have done the same thing. We get a raw product in, we fractionate it, we make a bunch of different intermediates and convert them to final products. The key thing here to note is we don't think about oil sands in terms of the price of gasoline at the end of the day. And sorry, let me back up. We tend to take things like gasoline, a price of barrel of gas, and compare that to ethanol. We don't do that. We talk about a barrel of oil and compare that to ethanol. And the problem with that mixture is that we've lost all the value byproduct streams that we could get from the ethanol process. Very much like if we have a barrel of crude oil, West Texas crude, the price value in that comes primarily from ethanol, but there is a 5 to 10% component that goes to very high value applications in the chemical industry. And we have to start modeling that a little bit better. Fuel ethanol, US reached 5 billion gallons in 2006. It's higher now, about 5.5. Some of the facilities are under duress, obviously with the economic setback. They want to get still to 30% by 2030. And if all corn in the US was converted to ethanol, it's only about 15%. So they are very quickly moving to the lignocellulosic conversion to ethanol and to some of the other fuels. Thankfully, over the last year, the US has started to break out of that mindset where they want everything into ethanol. They are looking at the next generation fuels rapidly right now. But one of the things we see is that there is opportunities for technology to play. If you went back even 10 years ago, the ethanol process was 1.2 energy conversion, which meant you need 1.2 units of energy to get 1 unit of energy of fuel out. It made no sense, and you heard a lot of complaints about this. With advances in enzymes, etc., you went from 67, a ratio of 0.67, which means you're now getting more energy out than in, up to 0.3. So this is about 3 times more energy out than you're putting in. And the reason for this is they've done things, which I'll talk about in a second, but they go to lower energetic conversion processes, and they've also moved to more advanced enzyme systems. One of the issues is, again, you look at starch and the form that you find it in different biomass, it's in different structures. So to move to non-traditional, you have to be able to advance the enzymes used. What I wanted to focus on quickly is this is the traditional ethanol process. I won't go in a lot of detail, but you can see it's it's a multi-stage process. They inject steam to rip the starch apart that I was just mentioning. This costs you a huge amount of energy in your process. It also damages those other components in the crop that may be used for value extraction. Okay, and then you go through liquefaction, and eventually you ferment and you get your ethanol. Again, you guys don't want to spend a lot of time on this. But what the newer processes have gone to, and these are what we've mimicked in our lab, both of these, and working with the companies like Syngenta, Novozyme, and Genicor, the major enzyme companies in the world, you can go to processes that remove those high temperature heat treatment steps. This is where you're getting those huge savings in energy, and it comes from using enzymes that are much more aggressive, much more robust. And we basically can go directly to fermentation without getting at high temperature.